All right, so now we are moving on and we're going to look into talking about Newton's second law. We extensively covered Newton's first law, and so we are going to up our game and talk about things that are not moving with a constant motion. So today, when we get done with this, we should be able to state Newton's second law, both in words and mathematically. We should be able to determine the net force acting on an object using Newton's second law, and also use the net force to determine the acceleration of an object. So Newton's first law is a model we use to describe objects that are at rest or moving with a constant motion. So we're talking about things whose motion is not changing. When Newton's first law applies, we say that the forces acting on an object are balanced. But sometimes we are looking at an object whose motion is changing. When that happens, Newton's first law does not apply. We know from our last unit that an object accelerates when its motion changes. Remember, this is if it is slowing down, speeding up, or changing direction. This is essentially what the end part of Newton's first law refers to. When we have an outside force, we have a change in motion. Outside force is outside force, let me get my words out. Outside force is often how we see it written, but better way to phrase it would be to say that there is a net force acting on the object. Even if you don't know it, you probably have enough background knowledge to know that if you have a higher net force, then the change in motion of an object will be more. Give your chair a little push and it might scoot just a little bit, but if you give it a bigger push, it will move further. This is what we mean when we say that the change in motion of an object, or its acceleration, is directly proportional to the net force applied to it. If the net force goes up, then the acceleration will go up. Remember that we called Newton's first law the law of inertia. Inertia is the tendency of an object to keep doing what it's doing. And the heavier the object, the more difficult it is to get it to change its motion. So an object's acceleration also depends on its mass. So the more mass something has, the less its acceleration will be. This is what we call an inverse relationship. So something with a high mass will be more difficult to change its motion. So Newton came up with the second law as a model to describe an object whose motion is changing. Newton's second law says that an unbalanced force results in a change in an object's motion. Remember, we defined changing motion as an acceleration, and this means that the object can be speeding up, slowing down, or changing direction. In this situation, in all of these situations, net force is the overall push or pull. So remember our tug of wars. Now there's somebody winning our tug of war. So acceleration is when the motion of an object is changing, okay? And then the mass is the amount of matter in an object. And something to keep in mind is the acceleration is always going to be in the same direction as the net force. Now we can take these two relationships and math them together. I'm not going to go through that whole situation here, but instead we're going to wave our magic algebra wand and put these two relationships together into one expression. Mass has an inverse relationship with the acceleration. Notice if the mass is increased, the number in the denominator increases, and this makes the acceleration smaller. And if you give something a larger push, it will move faster. So increasing the net force will increase the acceleration. This gives us a lovely equation that says the acceleration is equal to the ratio of the net force applied to the mass of the object. Now, a lot of times you will see this written as the net force is equal to the mass times the acceleration. This is the same relationship, it's just rearranged to show the net force. In this relationship, mass represents kilograms, and it's represented by the letter m. A is the acceleration in meters per second squared, and net force is the net force, or F net is the net force in newtons. So let's try an example. A 650 kilogram car accelerates at 4 meters per second squared to the south. What is the net force acting on it? So the first plan of attack should be to write down everything that you know. We were given the mass of 650 kilograms, and we were given the acceleration of 4 meters per second squared south. So then we're trying to find the net force. So which equation would be the best one here? Since we are looking for net force and we know the mass and the acceleration, the F net equals ma seems appropriate. So the net force is equal to 650 kilograms times an acceleration of 4 meters per second, and this gives us a net force of 2,600 newtons. Now don't forget that a force is a vector, so we need to include the direction. The acceleration was to the south, so the net force will also be to the south. Let's try this one. A 5 kilogram block is pushed to the right along a frictionless track with a force of 10 newtons. What is its acceleration? So in this problem, we are given a massive block along the force applied to it, and we want to know the acceleration. So we want to use the acceleration form of Newton's second law. But what is the net force? A lot of times it's a good idea to sketch out a force diagram to help us visualize where the forces are going. We are on Earth, so we have gravity acting down on our block. And since it was not stated otherwise, we can assume that it's a level surface. And so the normal force would be pushing straight up. So since the force of gravity and the normal force are the only two forces acting in the vertical, we can say that the vertical forces are balanced and that there is no acceleration either up or down. Now the applied force is acting to the right, and there's no friction acting on the track to take away from that. So the net force acting on our block is completely due to the applied force. Remember that we typically refer to the right direction as the positive direction. So the net force acting on the block is 10 newtons to the right. Now we know the net force and the mass, so we can plug that into our equation. And we have 10 newtons divided by 5 kilograms. And that's going to give us an acceleration of positive 2 meters per second squared. So to summarize, we have talked about net force. Net force is the overall push or pull on an object. We've talked about Newton's second law, and we've described it in both words and mathematical form. We know that Newton's second law applies to an object that is changing its motion or accelerating. And we can determine it using the mass and the acceleration. And we can determine the direction of an acceleration by determining the direction of the net force.